All right, you guys, I'm going to break down some periodic trends on the periodic table, meaning like what happens to things as you go across a group or across a row and down a group. So there's 5 different trends that we're going to look at, and I'm going to kind of break it up with this worksheet, looking at what's the definition, what's going on in the period, meaning in the row, and what's happening in the group, meaning going down a column, and then we're going to kind of have a picture for some of them to look at. If you're confused on any of this, you can find this on page 290 in your textbook. So if you need to look that up, and it's also in your separate Chapter 7 notes. Each one of these trends is broke up there too. So let's kind of take a look at the definition of atomic size. The definition is the distance between atoms in a chemical compound. And I'm hoping you guys can read this. My handwriting is terrible anyway, but this makes it a little bit worse. So it is the distance between atoms in a chemical compound. So basically it's just the size of an atom. That's what we're looking at here. So as we go across a row, size actually decreases. I'm just going to show this as an arrow as you move left to right. So you may want to have your periodic table in front of you. So as you go across a row, for instance, if you go across row 2 and you look at lithium versus carbon, lithium is going to be a bigger atom than carbon because the general trend is the size of that atom will get smaller as you move from left to right. Now, the reasoning here is something called, and the symbol that they use for it is Z and subscript ZFF. That is nuclear charge. So as you go across that row, you're adding a proton. So, and you're staying within the same, and I'm going to kind of draw this up here, you're staying within the same energy level. If this is the nucleus, you're adding one more proton, but it's kind of staying within that energy level. It's either an energy level 2 or energy level 3 because each row is an energy level. So it's staying within that row, so that nucleus in the center here has a much stronger pull on those electrons, and it'll pull them down tighter, and it'll cause that atom to be smaller. So that is what's causing the size to decrease. But as you go down a group, down here, size actually increases as you go down a group. And the reasoning is kind of the same because you're looking at that nuclear charge, that EFF. I don't exactly know what that stands for. It just means nuclear charge. So what happens is, as I go down a group, I'm increasing my levels. I'm going from, if you look at it, maybe level, if the nucleus is in the center there, level 1 to level 2 to level 3. That nucleus is not able to have a strong pull on it, so it kind of allows that atom to get bigger as those electrons, and you're adding more levels, so the atom is getting bigger anyway. So that's kind of the general trend. So what I would ask you is, let's draw the picture first, and then I'll give you an example. So picture-wise, I'm thinking this is what the periodic table looks like. So size is going to actually decrease this way as you go to the right, and size will go up as I go down a group. So I'm just going to kind of give you an example. Like if I start over here and the atom's that size, as I go across, the atom is just going to get smaller and smaller as I go across. And then as I go down a group, those atoms are going to just get bigger as I go down a group. So some questions I would ask you would be like, okay, take a look at phosphorus, sulfur, and chlorine. I'm giving you a couple easy ones. And I ask you which one is smaller or which one is larger. So let's go with which one of those atoms would be the smallest. Well, chlorine would be the smallest because it sits all the way to the right. So as I go across that row, those atoms get smaller. So phosphorus would be the biggest one. Chlorine would be the smallest one. Those are the types of questions that you need to be able to answer for that. So let's go on to the next trend. It's ionization energy. I kind of keep these 2 trends together. If I can understand which atom is smaller and which atom is bigger, I can also answer this question. But to define it, ionization energy is the energy required to remove an electron. And I'm just going to put E- from an atom. So that would be like if I have an atom and it's going to get stripped of an electron, it's going to lose an electron. Metals tend to do this. So there is a general trend for this. So I'm going to kind of talk about the general trend, and then we'll kind of talk about specifically some of these. But before I do that, I want to kind of take a look at aluminum. So I'm going to do an example down here. Aluminum's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. So what happens here is if aluminum loses one electron, and this you just need to have in your notes, it'll kind of make sense as I go on. If it loses one electron, what happens is it actually takes 580 kilojoules of energy for that one electron to be pulled from that atom. But if it were to lose another atom, so starting with aluminum 1 plus, and if it loses one more electron and it goes to aluminum 2 plus, that's a bad 2, plus another electron, it actually takes 1,815 kilojoules. And it takes a lot more energy because that atom is already charged here. It's already aluminum plus. So it's already charged. It makes it very hard to remove that electron. And if I keep going, say aluminum 2 plus loses another electron, which we know aluminum typically is 3 plus. So it will lose 3 electrons, but it takes energy. It takes a certain amount of energy for each electron to be pulled. This one actually takes 2,740 kilojoules to pull that electron from that element. Now, if this actually tried to go on and 3 plus tried to lose another one and it tried to become 4 plus, it would actually take 11,600 kilojoules of energy, which it's unable to do that. It's too hard for it to do that. So it's going to stop right there at that point, and it's not going to lose that because that's way too much energy to try to pull an electron. The reasoning here is, and I had this wrong. This is 3s2 up here. So here are the 3 electrons that it's losing. Once it loses those 3, it's going to be really hard to pull it from that 2p orbital that's already filled. That's why it takes 11,600 kilojoules. So I just kind of wanted to explain that. You know, it does take, there's something called first ionization energy, second ionization energy, and third ionization energy. We're just going to look at, typically for our trend up here, I'm going to start with periods up here. We're going to be looking at first ionization energy. So there's a general trend. So it generally, that means there's going to be some types of an exception when I say generally. It generally increases as you move left to right. Okay, and the reasoning here is, it's going to be, think about the size. So think size. I'm going to put that hint there. Think size. The smaller the atom, the harder it is to remove an electron. Because think about magnets. When magnets are actually stuck together, it's harder to pull them apart. So if it's harder to pull them apart, it's going to take more energy to pull them apart. So the smaller the atom is, smaller atom, higher energy. Think of it that way. So if you can't figure out this trend, it ties in with atomic size. So on down here on the group 1, the first ionization energy, it will generally, meaning there's exceptions, decrease as you go down a group. And again, same reasoning. Think of the size. Electrons are easier to remove if atom is bigger. I'm running out of room here. So it'll be easier to remove an electron from an atom that's bigger. So it takes less energy for it to do that. So as far as your picture here, I kind of think of this one with size. So yes, ionization energy goes up as you go this way, and ionization energy goes down as you go down, or it goes down as you go down that group. I think of it as, I kind of have my size of atoms. So if I've got one and it's going to get smaller and smaller as I go across, I think of that smaller one all the way on the right taking a lot more energy to remove that electron. Whereas I go down a group, it's going to be way easier to remove an electron from that one right there because that atom is so big. So there are some exceptions, and I'm going to kind of write them in a different color at the top of the page here. So you've got a couple of elements, like say nitrogen. Its electron configuration is 1s2, 2s2, and 2p3. Oop, that's a 3. And then oxygen is 1s2. Why is it erasing? 1s2, 2s2, and then 2p4. So generally the trend, if you look at these two elements, nitrogen is supposed to have less energy than oxygen, but actually oxygen ends up having less energy. There is kind of an exception to this rule. So if you think about this p orbital that has 3 electrons in it, this p orbital has 4 electrons in it. So for oxygen, it's going to be much easier to pull that electron than the one in nitrogen, because it's just that extra electron in that orbital. So it's going to be easier to remove. So there is an exception to this one between nitrogen and oxygen. And then if you look at your periodic table, it's going to be the same for phosphorus and sulfur, and then for arsenic and selenium. So then another one I'm going to do in a different color would be beryllium, which is 1s2 and 2s2. And then boron is 1s2, 2s2, and 2p1. Now, if you look at the location of these on the periodic table, beryllium is to the left of boron. So technically, beryllium should have higher energy, but it doesn't, because if you look at this electron configuration, it's going to be much easier to take that electron from that 2p orbital than a full 2s orbital. So boron is actually lower energy because of that. So the exceptions for that, if you look at your periodic table, are beryllium and boron, and then magnesium and aluminum, and then calcium and gallium are big ones that will do that. So this is all in your separate Chapter 7 notes too, if you want to look through those. I'm mostly just going to cover this, but that is actually covered in that if you want to look through your notes. All right, the next one we're looking at is electron affinity. I'm only going to briefly touch on this one. I haven't seen a lot of questions from it, so I think you're going to be good if you just kind of understand that trend, but I don't think there's going to be a lot of questions about it. So don't get hung up on this one. So this is the energy change associated. So I'm just going to put associated with the addition of an electron. So kind of the opposite of ionization energy. This would be if it's gaining an electron. So if I've got an atom and it gains an electron, and it becomes now X minus. So it's gain an electron. The trend for this is, and I'm just going to put EA for electron affinity. So this increases as you go left to right. So the reasoning here is, why does it increase? Because it has to do with the nuclear charge again. It kind of always has to do with the nuclear charge. If that atom is smaller and those protons are pulling in on those electrons, it's going to be able to kind of think of it as like suck another electron away from another atom. So it's going to be able to pull that electron in because the protons are so close to that outer level where it could pull an electron in. So smaller atom would have higher electron affinity. So kind of the same as ionization energy, but it's just dealing with whether this atom is losing electrons or gaining electrons. So then the trend going down, electron affinity decreases as you go down a group. Reasoning here is because it's same thing, the size of the atom. So if it's a bigger atom, it's kind of hard for that proton because it's so far away from that outer level where the electron needs to be. It isn't able to pull that in. So larger atom has a harder time pulling electrons in. Okay, I don't really have a picture for this one because it's kind of, again, if you want to draw it, it's kind of the same. Electron affinity goes up as you go to the right, and electron affinity goes down as you go down a group. It's kind of the same as ionization energy. So that's kind of all I want to discuss with that one because there's not a lot to that. The next one I want to look at is ionic size. So ionic size, and I'm going to kind of do this in a different color. I'm not sure I like green. Let's go blue. So ionic size is what you have to think about it. I've covered atomic size. Well, ionic size is going to be the size of an atom after it becomes an ion. So you have to understand what an ion is. It's going to be the size of an atom after it loses or gains electrons. So you learned about this in physical science, but you've got cations, which they've lost electrons, and you've got anions, which have gained. They gain electrons. So cations are your metals on the left side of the periodic table. Your anions are the nonmetals on the right side of your periodic table. So the trend is going to be kind of the same. There are going to be some exceptions on whether something is becoming a cation or an anion, but basically the size will still decrease as you move left to right. But you have to understand, when you're going across a row, you're moving from metals to nonmetals. So they're going to be doing something different. But overall, generally, the size will decrease as you move left to right. And then again, the size will increase as you go down a group. So as you go down that column, your size typically will get bigger. So potassium is bigger than sodium. Well, sodium's ion is still smaller than the potassium ion, is what I'm trying to say. That is the general trend. So I don't really have a picture, but I need you to kind of, what we're going to do below is kind of describe what's going on with cations and what's going on with anions. So I'm going to do each one in a different color. So we're going to do cations first. So again, I talked about cations, but what happens is cations actually shrink, meaning their atom shrinks in size. It gets smaller. So it shrinks because the nucleus is attracting less electrons. Meaning cations have lost electrons. So it now has one more proton than it does electrons. So now that it has an overabundance of protons, that nucleus is able to pull everything in closer and kind of shrink that size down. So for example, what I mean, and I kind of talked about this one, if this is the size of sodium and this is the size of potassium, what happens is the sodium ion gets smaller. The potassium ion gets smaller. But again, the potassium ion is still bigger than the sodium ion, and I didn't draw that one the best. My stylus is kind of hard. The same thing would happen if you had like magnesium and calcium. So they're going to be like, there's magnesium, there's calcium. Obviously, calcium is bigger than magnesium because it's below it on the periodic table. That's its atomic size. But when you're looking at its ion size, it's going to be smaller. Magnesium will still be smaller than calcium. But again, when they move from their atom to their ion, they shrink in size. So this would be Mg2+, and this would be calcium 2+. It's lost 2 electrons. So every time it loses an electron, it gets even smaller. Okay, so then on the flip side, when we're looking at anions. So anions, they actually expand, meaning they get bigger. They expand since the nucleus, I can't draw, since the nucleus, that was a really bad sense, is now attracting more electrons. Okay, so what happens is if I've got an oxygen atom, when it gains, if you look at the periodic table, oxygen gains 2 electrons. Well, now it's going to become bigger. So this is the oxide ion. It gets bigger than its original atom. So then fluorine, a fluorine atom maybe looks like that, and then fluorine 1- is going to get bigger than its original atom because it's now gaining more electrons. That nucleus doesn't have a strong pull on it anymore, so it's able to get bigger. So you're going to have to think through some problems, and I'm going to kind of maybe write them up here. So if I said, you know, which one of these would be bigger, are we looking at maybe nitrogen ion, or is the beryllium, which becomes 2+. So what you have to think about is the overall atomic size is that it does get smaller as you go across. So really nitrogen should be smaller, but now we're talking about the ions, and we're talking about this guy gaining 3 electrons and this guy losing 2 electrons. So really the bigger atom or the bigger ion here would be nitrogen. That would be the larger one. So I'm going to work through some practice problems so you guys can see this, but I just kind of wanted to explain this, that you do have to understand what's happening when something becomes an ion. Does it get bigger? Does it get smaller? So we're going to move on to the last trend. So we're looking at electronegativity. This is actually covered in Chapter 8. So I'm going to go ahead and cover it here because I think it just makes more sense to have this in here. Electronegativity definition is the ability of an atom that's, why does it keep erasing? Atom in a bond, having technical difficulties, to attract shared electrons. Okay, so electronegativity, the trend is electronegativity increases as you move left to right. So I think of this one as the ability of an atom to want to take on electrons. So when I think about elements on the right side of the periodic table, those are my anions. Those are the ones that want electrons. They want to gain electrons. Now, on the left side of the periodic table, those are metals. They don't want to gain electrons. So it is, I mean, if you look at the trend, electronegativity, when I go across a row, so let's look at row 2, when I get all the way over to fluorine, fluorine is actually your most electronegative element. And the reasoning here is we have to ignore group 18 at this point because the noble gases, they don't want to gain any electrons. So fluorine is your most electronegative element over there. It is the one that wants to attract electrons the most. It only needs to gain one electron. So it's extremely electronegative. So then on the flip side, when I'm looking at a group, electronegativity decreases as you move down a group. So if I look at this, if I look at my first group, because if fluorine is my most electronegative element, my least electronegative element is going to be all the way at the bottom of group 1. So francium is my least electronegative element. It doesn't want to gain any electrons. So it's the least electronegative. I don't really have a picture for this one. You just kind of have to know these trends. But it does have something to do with the nuclear charge and whether it wants to gain electrons, how many valence it has, and what type of pull it has. So again, think of fluorine as being, fluorine just needs one electron. It has 7 valence electrons. It just wants one. So it's very electronegative. Whereas francium and all those elements on the left side of the periodic table, they don't want to gain any electrons. So they just don't. So that is your trends. I am going to work through some practice problems, and then you're going to kind of have an assignment over these trends. If you're having trouble with it, please let me know. Also refer to your notes, your Chapter 7 notes at the end where they do talk about trends. There's a lot of good information in there, but I wanted to break it up just a little bit different to kind of help you guys. So I'm not going to go through those notes, but I'm obviously going to work some practice problems and go through maybe a couple of your examples on your assignment. We'll see. Okay? If you need any help, let me know.